This video is on section 4.4 notes, more equations and applications. And of course, we're still in the context of logarithms and exponentials. And so those are the types of equations and applications we'll be working with. So first, we're going to look at some logarithmic equations. Before we even really begin, I put a note here that says you cannot take the log of 0 or a negative number. And that's because if you think back to the little chart we had on a previous set of notes where I showed you guys, reminded you guys really how exponents work, even if you use a negative exponent, you never get 0 as a result. Even if you use a negative exponent, you never get a result that's negative. Even if you use 0 as an exponent, you still don't get 0 as a result, or a negative answer. So because we can't get answers of 0 or negatives when we're working with exponential functions, then when we work with their inverse functions, that means that we can't plug them into a log either. So when we're solving logarithmic equations, we have to be aware of extraneous solutions. And extraneous solutions are those that we would solve for, we'd find them, but then when you plug them back in, they would end up making you take the log of 0 or take the log of a negative number, and it wouldn't be possible to do that. So that's what we're going to watch out for. These first two types of logarithmic equations are probably the most intuitive. If you have a log on each side of the equal sign and those logs match, they have the same base, then you can kind of ditch them and just solve the equation based on what was inside the log. So here we could say 4x equals x plus 6. And this is a linear equation, so I'm just going to get the x's to one side. So 3x equals 6. And I'll divide by 3. And x equals 2. And then I just want to make sure that if I plug 2 in, I don't get 0 or a negative number. So 4 times 2 is not 0, it's not negative. 2 plus 6 is not 0, it's not negative. And so I know that this is not an extraneous solution. This is a valid solution. All right, over here, we have ln on the left side and ln on the right side. Both of those are log base e. And so I can get rid of the logs. And I'll look at the remaining terms. 2x equals 24 minus x squared. This is a quadratic equation. I can tell because there's an x squared in it. And so when I solve a quadratic equation, I have two options. I can factor it or I can use the quadratic formula. And either way, I like for the quadratic to equal 0. And when I factor, I like the x squared term to be positive. So I'm going to take these terms and I'm going to shift them to the left side of the equation as I make my equation equal 0 here. So I have x squared plus 2x minus 24 is 0. And I'm looking for two numbers that multiply to negative 24 and add to 2. And the numbers that would do that are 6 and negative 4. So my factors are x plus 6, x minus 4. So the two solutions I've come up with are the opposite signs of those factors, negative 6 and positive 4. And I just need to plug both of them in and make sure they don't equal 0 or a negative inside of the log. So 2 times negative 6 is negative 12, and so that's a problem. Negative 6 cannot be used. It would have been a problem here as well. 24 minus 6 squared, negative 6 squared is 36, so 24 minus 36, that would have been a problem as well. So we can't use the negative 6. However, with the 4, we have 2 times 4, and that's not 0, and it's not negative. And then we have 24 minus 4 squared, so 24 minus 16, which is not 0, and it's not negative. So 4 is a good solution, but negative 6 does not work. Sometimes I have students who internalize that if they see a negative answer, they can make a guess about it. And what I will say is that you will find that extraneous solutions are negative more often than they are positive. So some students will notice that, and that is true. But not all negative answers are truly extraneous solutions. So you can't just make the assumption, oh, because it's negative, it's not going to work. You have to check it every single time. All right, for the next set of problems, we have a hint here. It says if the equation has more than one logarithm on one or both sides of the equation, use properties of logs to condense the logarithmic expression to a single logarithm. So if we have multiple logs on the left side or the right side, we want to condense it down so we at most have one log on the left side and one log on the right side. That's all we want to have. So here, when we look at this first example, we can see that the right side is fine. It's got log base 2, just one log over here. But on the left side, we have 2 logs. And so I'm going to use my property of logs to condense it down. Both of these are a log base 2, so I can condense them together. It says plus, and so that means I'm multiplying what's inside the logs. So I'm going to do x multiplied by x plus 2. And x multiplied by x plus 2 is x squared plus 2x. And at this point, I have one log on each side of the equation, and so I can go ahead and get rid of the logs. So I have x squared plus 2x equals 6x plus 1. And just like in the previous example, I have a quadratic equation. And so my two options for solving this would be factoring or the quadratic formula. And in either situation, I want the equation to equal 0. I prefer for my x squared term to be positive, and it is already. So I'm going to go ahead and take these terms and move them over to the left side. So I have x squared minus 4x minus 1. And when I look at that quadratic, there's nothing that multiplies to -1 but adds to -4. And so that tells me that this is a quadratic formula problem. So I have the negative version of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So 4 plus or minus whatever the discriminant is over 2. And my discriminant is -4 squared minus 4 times 1 times -1. The discriminant is 20. And 20 can be reduced. The square root of 20 is the square root of 4 times the square root of 5. So that's 2 square root 5. So we have 4 plus or minus 2 square root 5 over 2. So that square root 5 cannot be touched. But the 4, the 2, and the 2 can all be reduced. Those numbers are all divisible by 2. So we end up with 2 plus or minus root 5. And so now I just have to think about these two solutions. I have 2 plus root 5, 2 minus root 5. And I have to think about what would happen if I go back to the original equation and plug them in. Would I be taking the log of a positive or a negative number? So 2 plus root 5 is 4.2. So if I plug in 4.2 here, that's fine. 4.2 plus 2 is fine. 6 times 4.2 plus 1, that's fine. So 4.2, this first answer, that's a good answer. That's going to work. 2 minus root 5 is negative 0.2. So for the first one, negative 0.2, when I go to plug it in right here, it's not going to work. Negative 0.2 cannot be plugged in to the first log. So the first one works, the second one does not. And when you are solving your logarithmic equations and you have some answers that have extraneous solutions and some answers that don't, make sure that you do all the solution work and you show that you got 2 answers, but one of them works and one of them doesn't. So I've got all the work written on my paper and I'm making it clear which one should be considered in the final answer, but which one I still found and I just knew didn't work in the long run. All right, for the next one, we have 2 logarithms on the right side, so I know I need to condense those. And on the left side, I only have log once, but I do need to use my property of logs to rewrite it. So on the left side, we have ln of x squared. We can take the coefficient and move it to the exponent. On the right side, this is an addition problem, so that means we've got multiplication. X plus 3 times x minus 1. And so when I take those 2 parentheses, I can FOIL them. I have x times x is x squared. X times negative 1 is negative x. 3 times x is 3x. So negative x and 3x gives me 2x. And then positive 3 times negative 1 gives me negative 3. And now I have a log on both sides, so I can get rid of that log. And that leaves me with x squared equals x squared plus 2x minus 3. And this equation is kind of nice. It looks like a quadratic, but our first step can be to cancel out an x squared on the left side and an x squared on the right side. There's exactly the same amount of them, and so I could just subtract x squared and subtract x squared, and that gets rid of both of them. So we end up with 0 equals 2x minus 3. And to get the x alone, I'm going to take the 3 and move it to the other side. So 3 equals 2x, and then I'll go ahead and divide by 2. X equals 3 halves. 3 halves is fine here. 3 halves plus 3 is fine. 3 halves minus 1 is fine. So 3 halves is a good answer. Okay. For this next page, it says, if the equation has a single logarithm only on one side, use inverse operations to solve. So for this first problem, there's no properties of logs that we need to do. We only have the word log written one time, but it's not on both sides of the equation, so I can't just cancel out the log. I have to undo it by taking the inverse. And so first I'm going to write this as log base 10. I know that anytime a base is not written, that's what base it is. This is the common logarithm. And then to undo the log, I just need to put a base of 10 on the left side and a base of 10 on the right side. So base of 10, base of 10. So 10 and log base 10 cancel each other out because they're inverses. And I have x minus 3 equals 10 to the 4th. 10 to the 4th is a 1 with 4 zeros after it, so that's 10,000. And then I can go ahead and add the 3 to the other side. X is 10,003. And if I plug this back into the equation, 10,003 minus 3, definitely not 0, definitely not negative. So that's a fine answer right there. For this other problem, they use the common logarithm again, so we still have a log with a base of 10. And this is a subtraction problem, so I need to write this as division when I condense this together. So x over x minus 1, I'll go ahead and put my base there, base of 10. And then to start undoing the log so that I can get into the parentheses and isolate the x, I need to put a base of 10 on each side. So 10 and log base 10 undo each other. I get x over x minus 1 equals 10 squared, so that's 100. To make this not a fraction anymore, I can take the x minus 1 that's in the denominator and just multiply it. So times x minus 1, and those will cancel, and I just get x. 100 multiplied by x minus 1 is 100x minus 100. And then I'll get my x's to one side. So 1x minus 100 x's is negative 99 x's. And then I can divide by negative 99. So x equals 100 over 99, and I just need to double check and make sure that that answer is okay. So log of 100 over 99 is totally fine. 100 over 99 minus 1. 99 over 99 would be 1. And so 100 over 99 is just barely above 1. It's like 1 in a decimal. So we're doing barely above 1 minus 1. This is not 0 and it's not negative. It's positive. It's just a very small decimal that's positive. So this number works. It is not an issue. It doesn't make anything equal 0 or equal negative. And so that's a valid answer. Okay, so that's it for logarithmic equations. Basically, you need to make sure that you do properties of logs to condense your logs together. And then if you have a log on both sides, you can cancel them out. And if you have a log on one side, you need to do your inverse operations. Next, we have one more type of exponential equation we haven't worked with yet. So first, I'm just kind of reminding you of work that we've done already to solve exponential equations. So if we have something like this, we can use our chart and we can take numbers like 16 and 1/64 and rewrite them so they have the same base. And then once you have the same base, you can just get rid of the bases and solve the equation. Over here, if you have something where you can't rewrite the bases, a base of 10 and a base of 50, we can't rewrite those as something else. In this case, we would just get rid of the base of the exponent by using an inverse operation. So solving by using logarithms is the same thing as solving by using inverse operations. And so we would undo the base of 10 by doing the inverse operation, and then whatever we do to the left side, we have to do to the right side. And then we can get our answer that way. But there's a third type of exponential problem, and that's the type that looks like this. So you can't change the bases. 6 and 7 don't have something in common on that chart. But it's also difficult to think about doing an inverse operation because we need to undo a base of 6, but we also need to undo a base of 7. And that is usually a confusing thing for students. So I'm going to walk through how to do a problem like this. And I do these problems by taking the natural log of each side. And I just use ln, kind of like the change of base formula. I used ln for that as well, just because that's my favorite. If you want to do the common logarithm, the log base 10, that's fine if you use that one instead. If you want to do a different logarithm, you want to do like log base 2, that's fine as well. They'll all work the same way. So I'm just going to do this with ln. I'm going to take ln of the left side and ln of the right side. And so right now I have ln of 6 to the x equals ln of 7 to the x minus 1. And so I'm going to use my property of logs and take my exponents and move them to the front of each of these expressions. So I have x times ln of 6, and I have x minus 1, which is a group, and so I'm going to put it in parentheses, x minus 1 being multiplied by ln 7. And what I'm going to do next is get rid of my parentheses by distributing the ln 7. So the left side of the equation has stayed the same, and then this would be x times ln 7. I'll put it right here. X times ln 7 minus 1 times ln 7. And you can literally write 1 ln 7 if you want, or you can just write ln 7. And now what I'm going to do is get the x's to the same side. So I'm going to take this x ln 7 and I'm going to subtract it over so it's on the left side. So on the left side, I have x ln 6 minus x ln 7. On the right side, I just have that negative ln 7. So now between these two terms, I have a GCF of x. I can factor the x out. And so I'm going to do that because my goal is to isolate the x. I want to be able to get it alone. And so if I can take it from being in two different terms and pulling it out so there's only one x there, that makes my life a little bit easier. And at this point, I can just take that whole set of parentheses and divide it over to the other side. So I'm going to divide by ln6 minus ln7. Divide by ln6 minus ln7. So the exact answer with no rounding is negative ln7 divided by ln6 minus ln7. That looks crazy, so I'm just going to type it in and see what the decimal is. So to get the fraction on my calculator screen, I typed alpha, y equals, and now I've got negative ln7 over ln6 minus ln7. And I'm going to go ahead and just put 3 decimal places, 12.623. And so that is my answer. And these problems look kind of crazy, but they're very repetitive. It's the same process every time. And so you'll find that these are not as complicated as they might have seemed initially. So let's try the next one. I'm going to stick with doing ln on each side, but again, you don't have to do ln. You could do the common logarithm if you wanted, or a different type of log. It doesn't matter. So I'm going to do ln of the left side and ln of the right side. So I have ln of 3 to the 2x minus 1 equals ln of 5 to the x. And then I'm going to take my exponents because I have that property of logs that tells me exponents should move to the front and think of them as coefficients. So this exponent that's moving to the front is a group, so I'm going to put it in parentheses. 2x minus 1 is being multiplied by ln 3. And then for this other one over here, I just have x. And then I'm going to get rid of my parentheses by distributing the ln 3. So I have 2x ln 3 minus 1 ln 3, or you can just say ln 3, it doesn't matter, equals x ln 5. And I want to get the x's to one side and the non-x's to the other side. And so I'm going to take this x term right here, minus 2x ln 3. I'm going to subtract it over to the other side. So on the left side, I have negative ln 3. On the right side, I have x ln 5 minus 2x ln 3. And now I want to get the x's pulled out so that I have only one x, getting it closer to being isolated. So I'm going to take the x out and write what is left over. So ln 5 minus, if I take the x out, I'm left with 2 ln 3. And then to get the x alone, I can just take this whole chunk of parentheses and divide it to the left side of the equation. So x is negative ln 3 in the numerator and ln 5 minus 2 ln 3 in the denominator. And I can plug that in. So if you had done this with log base 10, your answer would look similar to mine, but instead of having ln, 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 you would have log base 10 for all of those. Or if you had done it with log base 2, then yours would look like mine, except it would say log base 2 for all of these logs instead of saying ln. So it's really up to you which log you have. Our answers might look different right here depending on which log we choose to use, but our final answer, that decimal answer, is going to be the same. So this gives us 1.869. 1.869. All right, so next we're going to do some applications. I chose to focus in on radioactive decay and half-life applications, and that's because they're related to the compound interest formula. So when compound interest, when we had compounded continuously as kind of the keywords in the problem, we had A equals PERT. The final amount was the principal or the starting amount times e to the rate times time. So there's a similar formula used which states the amount A, this final amount, of a radioactive substance remaining after T years, where A sub 0 is the initial value, so we're using A sub 0 instead of using P. So instead of principal, we have an initial value, A sub 0. And R is the annual rate of decay, and since it's decaying, it's going to be a negative value. So here we were talking about interest, and so accounts were growing. We had positive values for the rate. Here we're going to have negative values for the rate because something's going to be decaying or decreasing in value for that particular substance. Here's our formula. A standard measurement of the speed at which a radioactive substance decays is its half-life. And you've probably heard of this in a chemistry class. The half-life is the amount of time that it takes for 1/2 of the substance to decay, which means that 1/2 of the substance would remain. 50% of it's gone, 50% of it's still there. All right, so here's an example. Since dinosaur bones are too old to contain organic material for radiocarbon dating, paleontologists estimate the age of bones by dating volcanic debris and surrounding rock using potassium-argon dating. The half-life of potassium-40 is 1.31 billion years. If 92.4% of the original amount of potassium-40 is still present in the rock, then how old is the rock? And then as a result, how old is the dinosaur that is found near the rock? So these problems need to be done in 2 steps, because you'll notice that they're talking about the half-life of something. They're talking about the amount of time that has passed. They're talking about the original amount and 92% of the original amount. But nowhere in here did they say, oh, the rate of decay is this. So the reason they give you the half-life is so that you can calculate the rate of decay. You have to do it. So our first step is going to be to calculate the rate of decay. And then our second step is going to be to go back and do the problem. Okay, so first step is to find the rate of decay, find the R. So we're going to set this up, and this problem is kind of a pain because it's 1.31 billion years, and we've got to write that out with all the zeros. So we're going to say we have our initial value and our ending value, and we know this is half-life. So if our initial value is 1, then our ending value is 1/2 of that. I like to use these numbers just because it's pretty literal. I start with the whole thing and then I end with half of it. But if you want to make up different numbers, you can. You could say, oh, I'm starting with 100 and I'm ending with 50, if you want to think of percentages. Or you could say I'm starting with 20 and I'm adding with 10 and I'm ending with 10. However you want to do that is fine. So we have the starting amount, the ending amount. The rate is what we don't know. The time is 1.31 billion years. And 1.31 billion years, I have to put my zeros in here correctly, is this number. This is what we're going to be using. So this problem is going to look messy because of the billions here and what that's going to do to our values as a result. Okay, so we have the ending value is 1/2, the starting value is 1, e to the r times t, and the t is 1,310,000,000, written like this. Okay. So if I have a 1 here, it doesn't really do anything. So I'm going to kind of ignore that 1. My goal is to solve for r. So I need to get rid of the base of e, and I can do that by doing log base e on the left side and log base e on the right side. And if you recall, a log base e is really just ln. So I'm going to ln the left side and I'm going to ln the right side. I'm kind of ignoring that 1 just because 1 times anything doesn't do anything. If I had used something other than 1, then I would have had to divide that number first. So R times 1,310,000,000 equals ln of 1/2, whatever that happens to be. And then I'm going to go ahead and divide by the 1.31 billion. And this R value that I'm getting is not going to be very nice because of how large the number is that I'm dividing by. So ln of 1/2 divided by 1,310,000,000. And I get an answer that's in scientific notation. I'm going to write this down. -5.29 times 10 to the -10. So I'm writing it down, but I'm going to store this in my calculator just so it'll be easier to use. So I'm going to hit STO. And then I'm going to use R over here in green. You can see R above your multiplication button. And so I'm going to hit the green button and then hit the multiplication button. And so my calculator is storing that as R. So now every time I hit green button, multiplication button, every time I hit the R, it's just going to spit out that value for me. And I'll go ahead and put a little R with a circle around it. This is not like common to everyone in the world. This is like Miss King does this. This helps me keep track of what I've stored in my calculator. Okay, so now we have the rate. So now we can go on to step 2, which is to actually figure out how old that dinosaur bone is by figuring out how old the rock is, basically. So we have the initial value and the ending value. They said 92.4% of the original amount is still present in the rock at the end. So if we start with 100%, our initial value is 100%. Of the potassium 40 is present in the rock when the rock is like brand new. Then when the rock has aged, now 92.4% is what's left over. So I'm just using these numbers because I'm thinking percentages. If you wanted to do the decimal numbers, you could have used 1 and 0.924. That would have been fine as well. I have my rate. It's the number that I stored on my calculator. So I'm going to write this down, but I'm going to use that rounded or that stored decimal that I have. And then the T is what I'm solving for because I want to know how long it takes for this to happen. So I've got 92.4 equals 100 e to the -0.529 times 10 to the -10th, that R value that I just solved for, that times T. So for me to solve for T, I need to start moving stuff away from the right side of the equation. So I can divide by 100. 92.4 divided by 100 just makes this 0.924. And then to undo the base of E, I just need to ln the left side and ln the right side. So ln of 0.924 is this rate times T. And then I need to take that rate and divide it over to the other side. Okay, so ln 0.924 divided by R, the number that I stored as the rate. And this is how old we think the rock is, and so that's how old we would think the dinosaur bones near that rock would be. So T is 149,386 168.7, And they'd probably have you, since it was 1.31 billion years, they might have you round this to the nearest million, since none of this, we didn't have this level of precision here. But we can go ahead and write the whole thing because they didn't tell us how much precision they wanted in the answer. So it's approximately 149,386,168.7 years old. That's how old we think that the rock is and how old we think the dinosaur bone is next to it. All right, one last problem. The half-life of the antidepressant Prozac in an average man is 2 days. So 2 days after a man has taken the dose, half of the medicine is still left in his body. How long does it take for 95% of the original dose to be eliminated from the man's body? So not for 95% of it to stay there, but for 95% of it to be gone from the man's body. So again, we have to do this in 2 steps because they're talking about the time, they're talking about how long for the half-life, and they're talking about how much, but they're not telling us the actual rate. They're not telling us the R value in terms of a percentage, a negative percentage of decay that we can use to solve for this time it would take to have 95% of the dose eliminate from his body. So the first step is going to be to find the R. And we're going to do that by thinking about half-life. So I'm going to say, I'm going to have the initial value 1, and then 1/2 of the initial value. That's the half-life. The rate is what I'm trying to find. And I know that the time is 2 days. So I'll go ahead and plug that into the equation first. I'm going to write my equation up here. So I have 1/2 equals 1 e to the r times 2. I'm going to go ahead and just simplify this. I don't really need that 1 there. R times 2 is 2r. Okay. So you can do this if you want. We didn't do this on the last equation, but it might, make things feel a little bit more simple as you work them out. So the first thing I need to do to get to the variable, the r, is I need to undo the base of e. So I'm going to ln the left side and ln the right side. ln of 1/2 is 2r. And then to get the r alone, I'm going to go ahead and divide by 2. So r is approximately negative 0.347. Negative 0.347. And I'm going to write this as I do my computations, but I know when I go through to get my final answer, I'm going to kind of copy paste this because I don't want to round in the middle of a problem. So next I'm going to find the t. Determine how long it takes. Now they said 95% of the original dose is going to be eliminated. So if 95% is eliminated, that means that 5% remains. 95% eliminated means that 5% remains. So if I have my initial value is 100%, that's how much of the medication you get when you take it, we want to know when 5% remains at the end. We know the rate is negative 0.347. The time is what we're trying to solve for. So I have my final amount is my initial amount times e to the negative 0.347 t. And my first step to start moving things away from t is to divide by 100. 5 divided by 100 is 0.05. And then I want to undo the base of e, and so I'm going to do ln on the left side and ln on the right side. And then I need to take that rate that I found and divide it over so that the t will be all alone. Okay, so ln of 0.05 divided by, and I'm going to go up here, get it so it's highlighted, and press enter. So I'm just copy pasting that. 8.644. And this was in terms of days. That's the context from the problem. I know it's days and not years because the original problem said 2 days. So it would take 8.644 days for 95% of that dose to be eliminated from the man's body and for 5% of that dose to remain in the man's body.